So let's get one thing straight about quantum computers. We always hear that they're faster. But that word, it's not just wrong, it completely misses the point. It's like saying a submarine is a faster boat. It doesn't swim faster, it operates in a whole different dimension. And that's what we're diving in today, the real secret to quantum advantage. It has nothing to do with speed. To really get a feel for what's at stake, let's start with a number. That right there is 10 septillion years. Now that is the time it would take the most powerful classical supercomputer on Earth to solve one specific, very hard problem. To put that in perspective, the universe itself is only about 14 billion years old. This number, it's just an impossibly long time.
Okay, so you've got that insane number in your head, right? 10 septillion years. Well, Google's Willow quantum chip solved that exact same problem in about 5 minutes. I want you to really think about that. That isn't just a little faster, it's a leap of 30 orders of magnitude. That's a 1 with 30 zeros after it. It's just a completely different reality of computation.
And right away, this should set off alarm bells. We all know the ultimate speed limit in the universe is the speed of light. Nothing can go faster. So how do you compress 10 septillion years of work into 5 minutes without breaking physics? What's going on here? The quantum chip isn't running faster, it's doing something else entirely. The answer, the real secret sauce, is that we have to completely redefine what we mean by work. The quantum advantage isn't about moving faster through physical space. It's about performing a totally different kind of action, something we're going to call virtual work. So what on earth is virtual work? Well, picture it like this. A classical computer is like someone trying to find their way out of a maze. It has to try one path, hit a dead end, backtrack, and then try another path, one step after another. But a quantum computer, it gets to explore every single possible path in the maze at the same time. This massive parallel exploration happening in this hidden quantum possibility space, that is virtual work. And this really gets to the heart of the difference. You see, classical computers are stuck in what you could call thermodynamic time. Step A must happen before step B, which must happen before step C. It's linear. But a quantum computer, for the brief window that it can maintain its delicate state, operates in virtual time. It's a place where all these potential outcomes and timelines are happening at once, interfering with each other to find the answer. Okay, but how does a machine actually do that? I mean, what's the physical engine that's driving all of this incredible virtual work? Well, the answer is probably the most fundamental thing in the universe: light. But not exactly in the way you might be thinking. It turns out the work is done by these things called virtual photons. They're like little messengers of the electromagnetic field that let the qubits talk to each other without losing energy. And the whole computation is this incredibly precise dance, an orchestration of billions of light cycles, all interfering with each other in just the right way. So get this, the information isn't just being sent on a beam of light. The actual computation is happening inside the very structure of the light itself. Just let that sink in for a second. At its absolute most fundamental level, every quantum computation is an act of choreographing light. We are sculpting electromagnetic fields to perform this immense, parallel logical work inside of a tiny sliver of real, physical time. It's kind of beautiful, right? All right, so if we have this totally new concept of virtual work, it stands to reason we need a new way to measure it, right? How can we actually put a number on how good a quantum computer is at doing this crazy thing? That's where a new metric comes into play. Let's meet the virtual work constant, or TeV. Think of it as an efficiency score. It's a single number that tells you how much of this dense virtual work a quantum system is cramming into every single physical resource it has. In this case, every cycle of light that's zipping around inside of it. It's a measure of computational density. Now, the calculation might look a little intense, but the logic is pretty straightforward. First, you figure out the machine's raw potential, its physical heartbeat based on its qubits and frequency. Then you calculate its virtual breadth, which is just the insane number of parallel states it can explore thanks to entanglement. You combine those to get the total virtual work it's doing every second, and finally, you just compare that virtual rate to its physical heartbeat, and boom, that's your KV. So when you actually run the numbers for a system that's a lot like Google's Willow chip, you get a KVOP of around 107. And what does a KV of 107 actually mean? This is the wild part. It means that for every single, solitary, physical wobble of the electromagnetic field inside that chip, the system is performing over 100 distinct, coherent,
virtual operations. That is the insane density of quantum computation in a single number.
Okay, this is all fascinating stuff, but you might be thinking, why does this really matter? Is this just an academic exercise? Absolutely not. Understanding things this way, through virtual work and KIB, has some huge implications for actually building these things. You know, there's actually this really cool analogy to Einstein's special relativity. With relativity, you're moving through space-time, and your ultimate limit is the speed of light. Here, we're moving through a space of possibilities, and our limit is how long we can keep the quantum state stable. In relativity, as you get faster, time itself slows down because of a factor called gamma. Well, Kville is like an informational version of gamma. It's a factor that tells you how much computational reality you're packing into every second of actual time. So, yeah, this isn't just some abstract theory. This framework gives us real, tangible tools to push the technology forward. For starters, QUVE gives us a universal ruler. We can finally compare an ion trap computer to a superconducting one on a level playing field. It also gives engineers a single clear target to aim for. Do whatever it takes to make QUVE as high as possible. It even gives us new ways to think about fighting errors and understanding the fundamental links between information, energy, and physics itself. It's a big deal. So let's just zoom out for a second and appreciate what this new perspective really gives us. It's a pretty profound way to think about what computation even is. At the end of the day, anytime we compute anything, we're really just structuring energy in a smart way. We are choreographing light. A classical computer, that's like a simple step-by-step line dance. But a quantum computer, with all its virtual work and coherence, well, that allows for a dance of breathtaking, almost infinite complexity. And all of this builds toward one powerful unifying idea. Intelligence is light structured through coherence. It's the ability to create and hold together these incredibly intricate patterns of light that allows this immense computational power to exist. It might just be one of the most fundamental principles there is. And that leaves us with one final, pretty wild thought to chew on. What if this isn't just about computers? What if the universe itself runs on this principle? What if the reality we all experience, every single moment, is just the outcome of a cosmic-scale quantum computation, constantly collapsing an ocean of virtual possibilities into the one solid world we see? It's a question that changes how you see, well, everything.